The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So I'm hoping you'll ask some questions today because we've had the exam. If you have any questions about grading, the two TAs are the people to speak to. Ramis graded questions 1 and 2, and Peter graded 3 and 4, and they control things. I mean, I can help if there's an emergency, but they would be the right people to speak to because they know how they graded the whole list. Before you ask questions, can I just say why this truss? You remember this 6-sided truss tied me in a knot, and I'm hoping your MATLAB solution will untie that knot. The knot I was in was to find the mechanisms, to find convenient mechanisms, because we have, well, I thought we had 6 bars. It looks like we have 6 bars. But somebody pointed out after class that bar 6 is not very active. It's connecting 2 supports. It can't do anything. And actually, that 6th row of the A matrix will be all zeros. So our matrix, so if we include that, there was no use. It doesn't help. So our matrix then really comes from the 5 bars. So A is then 5 by 2 unknowns, 2, 2, 2, making altogether 8 unknowns. So 3 mechanisms, and that's what I'm hoping for. So when I unwisely drew that picture on the board at the end of the truss lecture, I was only looking for 2 mechanisms because I was thinking we had 6 edges, 6 bars, but really this bar, when I knock out the columns that correspond to that node and that node, there will only be zeros left in that row, and it's nothing. It correctly tells us that the stretching of that bar is 0, but we knew that anyway. Okay, so I'm hoping, I don't know if you've tackled the MATLAB question, and I also don't know whether MATLAB would produce for us. I mean, you should be able to construct A with a whole lot of square roots of 3 and over 2 from sine of 60 degrees and maybe 1/2 from sine of 30 degrees. A should look pretty nice, but what the solutions to these mechanisms are, of course, solutions to AU equals 0. And anyway, I'm hoping that we learn from this example. I hadn't intended so it's pretty small MATLAB. It's really just the creation of the matrix A. Okay. So that was a comment on that, which I added to the homework. Now I'm ready for questions about the homework, the exam, whatever. Yes, thank you.
The homework.
Oh, good.
Unfortunately, I don't think I understand quite well how the ATA matrix is formed for trusses.
For trusses, okay.
Because often for the other mechanisms, for networks,
yeah,
and or for mass and springs, you
right,
can actually look at the problem and write out
ATA immediately, couldn't you? Yeah. It's not quite so straightforward, and this is like more realistic. I mean,
so
yeah.
One of the problems in the homework was to write that one, and certainly you were trying to prevent us from writing the whole thing, I suppose.
I guess, yeah, but remind me what that question was. This was a 2.7 problem 1? Okay, let me just see what I'm asking for. So, okay, yes. So I only asked about A transpose A. I only asked you for the shape in that question. Oh, and then I asked you for the first row. Good for me. Yes, all right. I see, the first row. So, yeah, so I didn't put you to the agony of writing out the whole thing, but still, how do you get the first row? Good question.
I was figuring there was some sort of a
Yeah.
trick that you were about to say, oh, this is the sum of these.
Oh, I see. Now, well, it's not going to be so neat. Let's just think. We could do the first row of A and the first column of A, probably. Yeah. So what am I looking for in A transpose A? Because in, say, row 1. Okay, so row 1 of A transpose A corresponds to the first. Oh, so what is row 1? Yeah, this is worth thinking about. So this is A transpose A for trusses. And let's just, maybe we could even take this one as an example. If I looked at, if I number the nodes, if that's my first node, A transpose A, you remember, that's square. That tells us the edge part, the bar part is built into it, but its size is n by n. Its size is 5 by, no, its size is what? 8 by 8, right. It's got to do with the number of, okay. So its first row, what will its first row be about? Yeah, okay, it'll be about UH1, right? The first row of this A transpose A matrix will be about the first node, but more than that, that node has got two things, UH and UV, and we're putting H first. So I think that the first row of this, well, let's just draw it. Yeah, no, maybe I'm not saying. So let that be A transpose A. I see, yeah, right. No, I'm sorry. A transpose A will be multiplying UH1, UV1, and so forth. Right? Okay, good. All right, so now this is better. All I'm asking is, where do we know there are zeros in that first row of A transpose A? Where would we know that there are zeros for this problem rather than I won't redraw the one in the book, so I'm taking this truss. So if it's this truss, this is the first node, the bars are numbered like this, and of course, your MATLAB construction of A, you might multiply out A transpose A, because in MATLAB that would be so quick, and you could see what it looks like. And where would we expect to see zeros or not zeros in that? Let's see. A transpose A, so I'll have to think. So that, my instinct is that it should only connect to neighbors. So that I would imagine, but I've got, these are double neighbors, right? There's two people living here, right? That's you have to remember. So I see two people living here and two people at home. So I guess I would imagine 4 non-zeros for this problem in the first row. I would think that would have somebody on the diagonal. That would be what multiplies UH1 itself, and then maybe UV1 is involved, and these two guys. These two and those two would not be involved. Well, that's only a partial answer. I'm just telling you where the zeros are, I think, and you're really asking about the non-zeros, of course. Yeah, not so easy.
So in other words, it just almost seems as if you have to set up.
Maybe you have to do it. Okay. Yeah.
So there's no.
Yeah. At least. Yeah. I think first time better to do it. Yeah. And then but that's an excellent question, and maybe we will find a nice and if somebody does, let me know, a nice way to see that. Somehow I must have felt that was doable when I created that problem. Yeah. Okay. Yes. The other thing to say, though, that while I'm looking at A transpose A, is remember that it can be created by these element matrices. Yeah, that's important to say. So there will be 5 element matrices, right? Because I've got 5 bars. And the element matrix for this bar, or say for a typical bar, the element matrix for this bar will involve all the U's that are connected to this bar. So 2 U's there and 2 U's there. So it'll be 4 by 4, the element matrix here. So this will contribute 4 non-zeros to that first row and to 3 other rows. That 4 by 4 guy from this bar, do you know what I'm speaking about here? The element matrix, which is just, the element matrix is a cosine, sine, minus cosine, and minus sine, column times row. Cosine, sine, minus cosine, minus sine. This is the element matrix for this bar. Those are the cosine and sine of 60 degrees. And those positions are, those positions would be these 2 and these 2. So there would be actually 4 zeros coming after, and after here from those 2 and those 2. So this bar contributes to A transpose A, sort of stamps into A transpose A this 4 by 4 of non-zeros plus the rest zeros, stamps that in up there. This guy has its own element matrix. Now, what's different about the element matrix for this guy? Of course, it's got its own C1 probably, and this had a C2 for the stiffness constant, but bigger differences than that. First of all, it's a different angle, theta. Here the angle is 120 degrees. And also, there's nobody home down there. So it would be, if we were dealing with A naught, free stuff, it would be 4 by 4, like all the others. But because these 2 are fixed, those 2 displacements are fixed, effectively it will only contribute 2 by 2, a total of 4 non-zeros. But those will stamp in to A transpose A, overlapping this guy. Then the ones from these bars will not touch the first row of A transpose A, so they wouldn't touch the answer to the homework problem. Is that, so that's, you're seeing again another way. I don't, by hand, I don't know that you necessarily want to use these element matrices. I'm not sure. But it gives an excellent check. So one way to create A transpose A is create A, multiply. That's one way. Second way is create A transpose A element by these 5 element matrices popped into the right places. Yeah. I think this is like the computational science part of the course. It's the way you would, I'm really speaking about the way you would write the code, not the final result. So much of the course has been devoted to understanding A transpose A and the fact that it's positive definite, or in this case only positive semi-definite, because we have an 8 by 8 matrix whose rank is only going to be 5. So this matrix will have these same mechanisms, and I'm hoping to learn what they are. Yeah. Well, I hope that's a little help with that question. But basically, though, it's non-help, because I'm sort of saying you're on your own to actually, I don't have a super fragilistic way to construct a matrix, and that you kind of have to do it. But I'm glad you asked. Okay. Yeah. Yes?
Going off of this problem some more.
More on this problem,
I
okay.
was a little unsure about the sign convention.
The sign convention.
Can you write out, say, like the 4th row of A? And go
Yes. So let's see.
the angle on it.
Let's see. So I made a speech about sign conventions, right? and which was that I am too old for them. and the justification for that is the fact that they wash out in A transpose A. So if you do use the wrong sign convention in A, you won't see it in A transpose A if I change the whole thing. So yeah, so my sign convention is not really a convention. Our convention is to decide that movement that way is plus, and movement this way is plus. And here, similarly, that's a plus movement and that's a plus movement. That's our sign convention. If we always do that, then the A matrix is telling us how much this bar stretches. It's the matrix that gives us stretching from these 4 displacements. And then these, I think in this picture, if this is the later node and this is the thing, then that angle from the horizontal is the right guy to put there.
Then why do you have the minus signs
Here?
Yeah, because you've got it times right now, so positive up and to the left.
Well, I guess oh yeah, yes, I see. The question is what's the sign convention with this particular picture? Yes. Yeah, if this is node 1 and that's 2, then I don't like which is the way, yeah, your question is good. It looks, I think I've got it not right. If this is node 1 down below and 2 up above, then moving 2 positively would stretch the bar.
Right.
And I've got minuses there. So I've got the opposite signs. I've got there the signs that would go with this numbering, if that was node 2 and this was node 1. Yeah,
Okay.
You're right.
So
Good.
so that if the bars.
You have to, that's the only way I do it, is to think, will the movement stretch the bar? Then that's got a positive entry in A. Will the movement like that compress the bar? Then it'll be a negative entry, because our conventions are, if it stretches, it's positive. Yeah. E positive means a stretching, E negative means a compression, and then I just have to, yeah. So it takes a little patience, or it takes writing the code correctly once, and then, of course, it would do it for all these problems. Yeah, I think the TA in an earlier year actually wrote a code a truss code. Don't know what happened to it, but I could look for it.
And
Yeah.
so when you handle the forces
Yes.
on A bar,
Yeah.
you do the same thing. You just assume some horizontal and vertical forces on both nodes and see what it does.
That's right, and it will come out consistent. Yeah, if I take horizontal, if I take the same convention that forces that way are plus, that's a plus FH1, and it's a plus UH1, then I'll get A will go to A transpose. Yeah. So if I'm consistent that plus for the U's for the displacement and plus for the F's forces, then the correctly created A will give me the correct A transpose. But A transpose A has the ability to bury some of those conventions. Yeah. Okay. Good. Yes.
Right, this is,
Different.
no, sorry.
More.
Still a
Oh my
little
God.
bit more the same,
Okay.
sorry.
Yes.
But then how do you deal with the theta convention? Because if, say you're looking at that figure you have up there.
This one.
Yeah.
Yeah.
You know, you have your 120, you have your 60, 0.
Yeah.
And are you just going right back to 120 then for bar 4, or is?
I wish it would ask about bar 3.
Well,
Yeah, bar 3 was good. Yeah, right. Yeah, I guess here, what's here? Well, the angle must be theta, and then this will be right provided this number is what? Well, yeah, I've got to think it out again. Yeah, yeah, I just think it out.
The angle between the horizontal and like the
maybe, yeah, I won't try to, yeah, I won't. So I think it's really, you learn the point by thinking that through, those signs, yeah, yeah. So I think we've got it here, that if that's number 1, then we like plus signs here because positive displacements will stretch the bar. Right, yeah. And here the sign will depend on the angle, and it will depend on the number, which numbers, what number that one is and what number that one is. If I reverse the numbers, then I reverse the signs. Yeah. Good. Well, that's sort of part of computational engineering, isn't it? Like, keep track of the details, but of course, this 18085 course is also about big picture things, and that's what I'm hoping comes through even better. Okay, ready for another question on any topic. Thanks.
So I'm wondering about how you find the mechanisms.
Yes?
Like, for example, in the first problem in section 2.7, you asked
Okay.
to draw the mechanism.
Okay.
Is there a systematic way?
Well, no, but let's just try. Should we do problem 1? Was it problem 1 in 2.7?
Yes.
Okay, let me just draw that truss, and let's just talk about it. So, boy, I put a lot of bars in there. Okay, all right, so this is just one bar down to this guy, and this is one up to here. And was that everything? Okay, and then I've numbered them. Let me just copy the number here so that we can talk about them. Okay. And now I numbered the nodes 1, 2, 1, the joints, I should say, really, 4. Okay. All right. Let's just start, as I always do, by what's the shape of the matrix A? A is what? How many bars have I got? So help me through this now, because 6 bars. And how many unknown displacements have I got? 8. Okay, good. And have I got any rigid motions here? No. No, I've got 2. These are going to prevent all the rigid motion. So if this matrix, if A has rank 6, which we probably guess it has, I don't see, but you'd have to, there's an if there. Then 2 mechanisms, right? 8 minus 6 gives 2 mechanisms. Okay, and your question is how to find them.
Right, I can see one of them.
You got one? All right, which one have you got?
Well, if you move the top 2 nodes, say, like, to the right.
These guys. So tilt. So that's a mechanism that only involves UH1 and UH2 and none of the other U's. Okay, that looks good. So that's certainly one. Now we're looking for a second one. Anybody suggest one? No, let me just give everybody a thought. If you haven't already started on this homework, we're starting now. So yeah, so I'm looking for another mechanism. And of course, you might say, well, suppose these bars go this way. Suppose they go to the left. And you know that that's not going to do it, right? And why not? Why isn't that a okay second answer? Because it's effectively the same as the first. In fact, the mechanism U, how would the U for the one I've drawn and the U for this way, what would we see? Opposite sign. If this describes a U1H and a U2H positive, the other way they're negative, it would just be the opposite sign. No, nothing new. Okay, so now you've had a look. So tell me if somebody sees, to answer your question here, how do you see them? I don't know. Just look harder. It's like, you know, speaking French. You just say it louder, and maybe it'll work. But no, I mean, of course, we do have the possibility to create the matrix and look for solutions. But it's more fun to do it this way. And now, who's going to suggest another mechanism? Another, yeah.
3 and 4 can rotate about the bases.
3 and 4.
So 3 goes up and to the right, 4 goes down and to the right.
Wait a minute. What was that? 3? These nodes. Okay.
Not the bars.
These nodes. 3 and 4 do what?
No, 3's on the left, bottom left.
Oh, yes. Sorry. 3
Go up and to the right,
go up this way.
and 4 will go down and to the
I see. You're rotating. Yeah. So this guy goes sort of along this way. This is. You're taking that top square and turning it. Okay. So these guys will also turn, right? Yeah. 1 and 2 will move on your mechanism. Yeah. So okay. So the idea is take that top thing, and I'm allowed to turn. Let's see. I have to turn it. I have to keep this bar. Yeah. I cannot stretch it.
Right.
You can't stretch any bars. So when I do this turn, I can't just keep it in place and turn. No. But I'm going to turn it so that this one goes this way, and this one goes this way. And now, all right, you're responsible for telling me about the other two now. What do they do?
Well, bar 4 will
Keep its length? Ha!
Yeah, it will. This is a basic 4-bar linkage.
Okay, well, we're not allowed to use fancy words like 4-bar linkage, because somebody might say, what does that mean? Okay, does it? Do you see that? I think it does, but it's wonderful that if that's the original bar, and I bring this up a little, remember, and this down a little, I think that the new bar has the same length. You believe that?
Yeah, one movement will.
No. Some, but yeah. I mean, what happened there? Yeah.
Well, doesn't one of the.
Yeah. This is a good example.
Number 4
Yeah.
will shrink. Right?
Sorry.
In other
Yeah.
words,
I mean, certainly bringing that up tended to make the bar shorter, but then moving this down tended to make it a little longer.
So for as long as those two motions have the same
Right.
relative magnitude, and
Yeah.
be okay.
I think so.
Will 5 stretch? What happens with 5?
Well, see, that was the key. We went at 90 degrees to 5. And by going at 90 degrees, then the stretch in there was only that 1 minus cosine that was higher order. That's the key. And similarly here, all these, so that we're avoiding stretching by this trick. So maybe this guy is going down this same way, and this guy is going up that same way. Yeah, because then that bar is just translating. This bar is translating, and these two are doing the same thing, which I believe is not stretching. Is this the answer that maybe somebody already got and believed in? Yeah. So was to answer your original question, wasn't obvious, was it? But I think that is the right thing. Yeah. And actually, you could create the A for this problem. Well, it's a bit large, 48 entries, but because 4 of the bars are horizontal or vertical, you will have many, many, many zeros in the A matrix. Yeah. Yeah, it would be sort of fun to create the A matrix, and then this. So what is this displacement that I believe in? This U mechanism that we've talked about. Let's see, if I look at 1, that was positive, positive. If I looked at U at node 2, that was positive over but down. So horizontal but down. If I look at node 3, that's positive, positive. Yeah, 1 and 3 are just hanging on, and number 4 is like number 2, 1 and minus 1. I think that's the u which should solve a u equals 0. Yeah. Okay, but that's a good example. Yeah. Okay, so that's trusses. What else? What else? Thank you.
What are the angles for bar 5 and 6?
Oh, well, let's see. That's a good question, and now I guess yeah, well, the way I've drawn it at 45 degrees, which is what I wrote here, then I did build in, I did make that I did make this 45 or 135 or something, and 45. To get that, if that goes at 45 degrees, then this had better go at 135, right? So that has to be a right angle. If the support was over here, then the angle that would have gone off with was, changed. Yeah, so very good point that the numbers I've written down and the picture I drew required these angles to be those nice numbers. Yeah, I hope you like these trusses a little. I mean, you get a little freedom from, just you get some freedom to visualize the thing. Yeah. Good. Yes.
On that, how could a solution also be if node 2 were to collapse down on the node 3 and then node 1 collapse down on the node 4? Like 2 meets up with 3, 1 swings to the left temporarily, and then it can come back and then collapse on 4?
Maybe. Let me see. I thought you were going to say, could I have 2 and 3 go inwards and 1 and 4 go outwards? You don't like that? I would go with that. Is that any good? Well, okay. Yeah, linear algebra spoke there. It's a combination of the other two, yes. If we only got a two-dimensional. But, okay, I'm sorry to...
I'm not understanding
that one.
The tilting. Like when
okay.
It collapses, the
yeah.
entire tilt to not the first one we did, but the second one where
yeah.
bars 5 and 6 are moving.
Yeah.
It's not a different collapse. It's just I don't...
Okay.
I'm not understanding that.
That one, okay. But let me, I sort of, when you suggested one, I overrode it. Now, the one you suggested, when you told me, okay, bring these in, I thought, okay, these have to go out.
I guess my question, what's the picture that you're looking to make with the bars? And can bars collapse on each other?
They're not allowed to change length, so they can only swing around these pin joints.
Right.
So the picture of the one that I drew after your question would be these guys, this guy, let me draw the square as it was, and then these guys came in a little, these guys went out a little, and we got this. That's okay. I think this is legitimate. This is a legitimate one. And it's, every bar now is doing the same kind of thing that this one does. This moved a little, but this compensated and kept the length the same. Your question has led us to another nifty mechanism. It's good one to think about. Yeah.
I guess I don't understand how, what's the end result? The end result is that it collapses upon itself, right? I mean, is that why we call it collapse, or just to move it without it stretching?
Yeah, it's movement without stretching. Movement without stretching is the key. Yes. And then where does collapse come in? I guess, so I use the word collapse pretty freely. So the word collapse comes in because since it can move without stretching, there's nothing controlling it. It can move, well, if we stay linear, then I could make all those 10 and the thing would be even worse. Of course, the truth is that if I made those even 1 or 10, I would be out of the linear range. These all should be 0.01s or something. But linear, we don't know the difference. Yeah. Yeah, okay, I'm glad you got that suggestion. And now somebody correctly says that this one must be some combination of that. And what was the first movement? Oh, the upper 2. Which it must be, yeah. Amazing how many, put a few bars up there and you got it. Yeah. And of course, by the way, and don't let me get too far into this discussion, but who's the artist? Actually, is it Alexander Calder who has, what are they called? You know, they're, yeah, what is it called again? Well, he has those, yeah, that wasn't the word I was thinking of. But he's created these trusses, like with lots of bars and lots of nodes that have some special property, anyway, it touches on art, actually, this theory of mechanisms. Yeah, it's really quite interesting. But then linear algebra somehow tells you, just from these numbers, how many mechanisms you're looking for, which is pretty cool. Yeah. Okay. Open for more questions. You probably haven't looked ahead, today's lecture was I hope, and I left up there the central topics for the lecture, but I think correct that you haven't started on those problems to know what to ask. Let me ask you a question, which was not in the lecture. Suppose I wanted to use finite differences. It's a little bit like the one on the quiz. So on the quiz, we had c equal 1s and then c equal to 2. And you knew c had to be 4 by 4, so most people correctly got the diagonal as 1, 1, 2, 2, just by sort of common sense. But what would be a finite difference approximation to our equation? So suppose I didn't go to finite elements, but instead I stayed with finite differences, which would be completely fine in 1D, completely sensible. How would you create a finite difference thing for that? Let me just bring down a blank board and ask. So you see the equation? Let me write it again here. So I want to replace this equation with that has a varying c of x. Well, I won't worry about the right side. It's f's. What's my K matrix for using finite differences for this? We're going to create a finite element K matrix by the weak form Galerkin trial function net root that's coming, and very important, it's coming. It started today and will be completed Friday. But now suppose we were back up to finite differences. What would you take for finite differences there? Well, when the c wasn't there, what did we do? Then we just had second difference, right? And how did we get the second difference? It was a difference it was a first difference of a first difference. I guess I would probably approximate by u I plus 1 minus u I over delta x. That would be that. And what should I put for c of x? What would you suggest? C subscript I. So you would. So let's mark. Here's I plus 1, and here's I minus 1. In we're going to end up with those three guys involved. Okay, so this takes this difference, and then this one will take that one, and then I'll also have a ui minus a ui minus 1 over delta x, and somehow it'll be the difference of these differences. But now tell me again, what would be the really cool choice of C? What's your instinct? What value of C to take? Sort of average, yeah. I guess, I mean, you could take it just halfway. I think I would take C I plus a half there, just as being sort of right. And here I would take C I minus a half, halfway along its interval. And then the second difference takes the difference of those. So now I've got, I think that's what I would do. If that would be my typical finite difference equation. It would be the difference times its C, and I took its C to be symmetric. You could also have taken, if you wanted to stay at these points, you could do twice as much work and take, let me say, so either C I plus a half, or you could average the CI and the CI plus 1 over 2. And both of those would give you that extra accuracy that you pick up from sort of keeping symmetry where you should. Yeah, yeah. So I think, I mean, this would be the quicker one to put. That one would be okay too.
So in an exam problem where it was a step.
I'm just, this was just for your entertainment, not, yes, go ahead though.
No, when it was a step, now you're going.
When C was a step, yes, when C was a step.
It appears as if CI plus a half or CI plus 1 or anything would have been better choice.
CI plus a half, probably the step.
Yeah, because otherwise you get.
Yeah.
C does not occur in this. The average is in between two values.
Yeah. Let me ask you, what happens to this equation when C jumps? It jumped on the quiz, but I didn't require you to solve the differential equation, only to create the finite difference model, to create the A transpose CA, and most people did it fine. But suppose C jumps. I have some simple right-hand side like 1. It's not a jump in the right-hand side I'm interested in. It's a jump in C from 1 to 2. So this is a topic that the book does discuss, and maybe I might come back to it in the ordinary lecture. But while it's in front of us now, the quiz was sort of intended to help you with that. How do I interpret this equation when C has a jump? Well, it's actually, if you look at it right, there's no difficulty. That equation is a combination of this equation minus dw dx equals the 1, and the equation of C du dx equaling the w. I split it out for you in the last part, problem 4b in the quiz. I really helped you to say, okay, take these two separate equations. Yeah, and now you don't really have a problem. The equation for W, nothing is out of the ordinary there. Jump in C is not even seen. So then you've got the W. Now you have the C in it with its little jump. But how would so suppose I find W from the first equation. How do I find U? I just divide by the C. I just go and integrate. Yeah. What I'm saying, let me say it clearly now. If there's a jump in C, that's not a bad thing, because the point is there's no jump in C u prime. C du dx doesn't jump. W doesn't jump from a jump in C. If C jumps, let it. There is no jump in W, which is the serious unknown. there'll be a jump in du dx, and that was that E thing that you had on the quiz. There'll be a jump in du dx to compensate the jump in C, but W is good. That's the message of, so let me write that down. Even if C jumps, W does not. Does not jump. Yeah. So it's my point is, when you're looking at W, you're looking at the right quantity, and it deals. This is a sort of general feature that if you look at it right, it's not a problem. If you look at it wrong and try to write out that equation, take the second derivative of this is okay, but then if you try to take the derivative of the jump, you think, my God, there's a delta function sitting in my equation. What am I to do? Don't do it. That pair of equations is no trouble. Yeah. Do you see that point? That a jump in C is really okay. C equals 0 wouldn't be so good, right? If C went to 0, then you have got some problem here, because if C is 0 here, what's going on? So your material, should have some stiffness, some positive stiffness. 0 stiffness would be a problem. Negative stiffness would be where really a crazy material, where you add more force and it compresses on you. Well, okay, that's a tricky one. Okay, so that was a point I could make also in the lecture. Yeah. Other questions? How are we doing? I hope you find these review sessions, they give a chance to bring out more points. There's this. Let me say a little bit about Chapter 2, things that we abandoned without including in the lectures. One very important thing that we didn't touch was the nonlinear problems, where you have to, in the end, you have to solve a system of nonlinear equations. We've only had linear equations. Ku equal F is where we always got to. And we've certainly found enough, to discuss there. But how do you deal with nonlinear equations? Well, that's section 2.6, I guess. And the answer is Newton's method, or some version. There are many versions of Newton's method. So all I'm saying is that's an important topic, is how to deal with nonlinear equations. And the answer is usually some variation of Newton's method. Yeah, depending on how many equations you've got, how bad the nonlinearity is, and things like that. That's a case where coding is not so simple. Yeah, but important. Yeah, so that's one thing in Chapter 2 that we passed, because really this is where we want to be today. Yeah. Other topics, questions of any kind? Yes, thanks.
Also
This problem?
yes.
Okay.
When F here is 1.
Yes.
Always. But another problem maybe is delta function.
Okay.
In that problem, the delta x should be considered in this problem.
Right. Good question.
Here,
You're right.
what condition should we consider this delta x?
Yeah. Okay. So now suppose that delta of x was in delta of x minus a. The jump at a was there. What would change in there? Well, the 1 would change, right? The 1 would now be the delta of x minus a. So what am I seeing now? What's the jump situation now? Is there a jump in? Does W jump now from this delta function? Yes. It did not jump from the jump in C. That did not produce a jump in W. Why not? Because you have again, back to the jump in C, you have a bar of copper and you have a bar of steel. And they have different C's. But the force at that point, when it's in equilibrium, the bar is not falling apart, right? The bar is, the force is the same from above and below. Equilibrium holds. It's just that the force involves a C1 there, and down here the force involves a C2 multiplying the du dx and this stretching. So the stretching will change. Du dx, the stretching factor, will be different in the two materials, but the force won't be. You really have to keep straight what. Now, you asked about a delta function. Okay, so now if I hang a delta function there, that's like hanging a point load at a point. What happens at that point? Well, we don't have a problem with this. Well, W jumps. The force pulling up is not the same as the force pulling down because there's this extra point load. So the balance there and the balance there is, those aren't equal. There's a jump there because of the point load being put there. Yeah, so that produces a jump in W, but not a jump in U. Not a jump in U. The bar is still holding together. And since time's running out, I don't have to ask myself or ask you about the worst possibility that occurs to me, which is, suppose they happen at the same place. Suppose there's a jump in C and a point load. Do we want to face that? What would happen there? Suppose A was the place where this jumped. Suppose the point load was here. What's up there? Yeah, well, hey, we'll be able to do that. Okay, all right, so I'm putting the point load at the place where the copper and the steel meet. Is W continuous? Is the force the same above and below that joint? No, because there's this extra term from the weight. And then once you know the forces, then above the bar you're solving for U with 1C, and then below that point with the other C. So W has a plus and a minus, and C has a plus and a minus, and you're solving this one. Let me make them minus plus. So you're solving this one in one bar, one metal, and C plus and the W plus in the other metal. Yeah, so you can do it. So shall I just repeat what my overall message is? W is the right thing to look at. The combination C du dx is the right thing to look at. Because it's what sits there in that parentheses. Okay, good. So that's some review topics. We really have a lot of fun ahead now with finite elements.